Good morning, students. In this video, we can start the discussion about how to convert from context-free grammar to their equivalent push-down automata. So, in this video, we can discuss whatever the conversion procedure and also explain some example to conversion from context-free grammar to push-down automata. So first of all, we discuss what are the conversion procedure from context-free grammar to push-down automata. So whenever we want to convert from context-free grammar to push-down automata, so that particular context-free grammar must be in GNF. So that means so each and every productions in the context-free grammar must be starting their RHS with terminal production or with the terminal symbol and then contains any number of non-terminals. So that is the major restriction to conversion from context-free grammar to push-down automata by simply so that particular context-free grammar must be is in GNF format. In case the given grammar is not in GNF, so first of all convert context-free grammar into GNF format and then convert into their equivalent push-down automata. So after converting into GNF, so we use two simple rules to convert from context-free grammar to push-down automata. So those two rules are one rule is for non-terminal symbols, one rule is for terminal symbols. So here in the given grammar which contains any number of non-terminals, so we simply written that particular non-terminal or that particular production rule can be written as so del of q is a state del of q comma epsilon comma. For just assume there is a production rule is in the given context free grammar, so there is a production rule is a derives to alpha. So there is a production rule is a derives to alpha. So then this non-terminal related production rule can be written in PDA is del of q is a state and epsilon is any input symbol from the given grammar and a is this particular non-terminal. Then it can be written as q comma alpha. So that means a RHS can be written here and then go to same state q. So del of current state is q and there is some input symbol which may be a or b or 0 or 1 any input symbol from the given grammar and a is a non-terminal. So then it can be written as q comma alpha. So why here we wrote alpha means, so here there is a production from a derives to alpha. So that's why in the place of a we can written alpha. So this is the one rule to convert from context free grammar to PDA. So this rule is applicable for each and every non-terminal in the given context free grammar. So that means in case the context free grammar contains two non-terminals, then we can written q comma epsilon comma a equals to q comma their production of RHS, and in case q comma epsilon comma capital B is another non-terminal, then it can be written as q comma b RHS, production rule b RHS. So this is the first rule. And one more rule for conversion from context free grammar to GNF is used for terminal symbols. So that means in case whatever the terminals is in the context free grammar, for each and every terminal we can written as, for example we assume there is a terminal is small a, so then we can written as del of q comma a is equals to q comma epsilon. So here epsilon means we are performing the pop operation. Here epsilon means in non-terminal symbols, epsilon means which may be any input symbol, and here alpha means in the place of a we can push their RHS production into the stack. So this is push operation. For non-terminals we can perform the push operation, and then for terminal symbols we can perform the pop operation. That means whatever the top of the stack, so such information can be popped from the stack. So these are the two rules to convert from context free grammar to push down automata. So very simple procedure. Once again recollect. So for each and every non-terminal we can written as del of q comma epsilon comma that particular non-terminal is equivalent to q comma their RHS of the production. So for each and every terminal we can written as q comma terminal is equivalent to pop operation q comma epsilon. So these are the two rules. Before translating from context free grammar to PDA, so that particular context free grammar must be satisfies the each and every RHS, each and every production rule RHS is must be starts with terminal symbol. So this is the procedure for converting from context free grammar to push down automata. So now we observe some example how to convert from context free grammar to push down automata. So here the question is construct PDA for the given context free grammar. S derives to 0 BB. So S derives to 0 BB and B derives to 0S or 1S or 0, and test whether 0 power 4 is acceptable by this PDA or not. So this is the question. So that means first of all we convert the given grammar into PDA and then we can perform the simulation or testing for 0 power 4. So now let assume there is some PDA M equals to Q. Here this Q is the number of states. So actually conversion from context free grammar to PDA we are using only one state, that is just assume Q. And here these are the terminal symbols, that is nothing but input alphabet 0, 1 from the given grammar, and these are the stack symbols, whatever the symbols was used in stack operations, those are each and every non-terminal and terminal symbols. So here non-terminals is S and B, so that's why S, B, and terminals is 0, 1. So these four symbols are used in stack operations. And next, here del is a transition function and Q is a starting state and S is the stock symbol, that means stock end of top of the stack symbol, that means empty stack. S contains, yes, actually in last examples we assume Z0. So but here by default the stack contains starting symbol of the grammar, so that's why here we are indicating with yes. And Q, sorry, this is not Q, this is pi. So here there is no final state, so this PDA is accepted by the empty stack. Whenever the stack is empty then it will go for final state. So this is pi, not Q. So this pi indicates there was no final state. So now we construct PDA for the given grammar. So consider each and every production rule. So here first production rule is S derives 0 BB. So here S is a non-terminal, so that's why we can written as per rule 1. So del of Q comma epsilon comma S is equivalent to whatever the RHS of S, so that is Q comma 0 BB. So here 0 BB is the RHS of the S production, that's why in the place of S we can push 0 BB into the stack. So this is nothing but push operation. So this is the push operation. And next, here one more production rule is there, so that we are starting with non-terminal B. So that's why del of Q comma epsilon comma B. So their RHS contains 3 productions, that's why we can write each and every one. So that is Q comma 0S is one production and Q comma 1S is one production and Q comma 0 is another production. So in this process we can perform any one of these 3. So based on our requirement, in case our required input symbol is current input symbol is 0, then we can use this push operation. In case current input symbol is 1, then we can use this push operation. In case current input symbol is 0 and there was no need to using one more non-terminal, at that time we can use this push operation. So in the place of non-terminal B, so the possible push operations are 3 possible push operations. Based on our requirement, choose similar or our required push operation belongs depending upon the current input symbol. So this is the PDA or ID, instantaneous description, for second production rule. So till now all non-terminal related production rules was completed. So now we consider when read the terminal as the input symbol, then what happens. So here there are 2 terminals, 0 and 1. So that's why when read del of Q comma 0 comma 0, then perform the pop operation. So this is pop operation. Above 2 are push operations. So at the same way when read one more terminal symbol del of Q comma 1 comma 1, then also we perform the pop operation. So these are the 2 pop operations, these 2 are the push operations. So in second one we can use any one of these 3 based on our required input symbol. So these are the IDs or PDA for the given context free grammar. So here PDA was represented in instantaneous description format. So now perform the testing for the given string 0, 1, 0 power 4. So here 0, 1, 0 power 4 means here 0 can occur 4 times. So that's why 0, 1, 4 zeros. So now to perform any string simulation or testing through the given PDA is always starting with the initial state. Here initial state is Q. So that's why we are considering from Q. So here state is the Q, current state is Q, and top of the stack is S. Here there was no need of input symbol at currently. Whenever we are having multiple productions, then only we consider what is the current input symbol. Otherwise, there was no importance for the input symbol. Why? Because at the time of conversion from CFG to PDA, we are also consider whatever the current state and epsilon, that means any input symbol. There was no priority for input symbol and top of the stack. That's why at the same way here also we consider what is the current state and what is the top of the stack. So by default the top of the stack contains starting symbol is yes. So that's why, so now we can replace the combination of Q comma S. So that is ID1. So here this one. So Q comma S. So now in stack we can perform the push operation. So that is 0, B, B. So these three elements can be pushed into the stack. So that's why here stack can contain 0, B, B. So initially stack contains S starting symbol. This S is replaced by their production 0, B, B in reverse order. 0 is the top of the stack and remaining will be next bottom of the stack. So next. So now current state is Q and top of the stack is 0. And input is also 0. So as per ID3, we can perform the pop operation, that is Q comma 0 comma 0. We perform the pop operation. So that means initially stack contains top of the stack is 0 and remaining is B, B. So this 0 will be popped from the stack. Then remaining is BB on stack operation and stack elements. So next step, here current state is Q, top of the stack is B. So now we check what is the transitions for Q comma epsilon comma B. So here there are three transitions. So now based on the input symbol we can choose what is the appropriate push operation for this one. So here current state is Q, top of the stack is B, non-terminal B, and input symbol is 1. So that's why here current state is Q and top of the stack is non-terminal B. So now input is 1. So that's why out of these three productions, only one production having one combination. So that's why we can choose this particular push operation in this place. So that's why this B is replaced with 1S. So here stack also initially it contains 2 B's. So now this B is replaced with 1S. Next. So current state is Q, input is 1, top of the stack is also 1. So that means Q comma 1 comma 1. So from ID4 we can perform the pop operation. After performing the pop operation, remaining input is 4 zeros and remaining stack contains S, B. So here this one. So initially it contains 1, S, B. So now we are performing the pop top of the stack. So that is 1 will be popped from the stack, remaining is S and B. So now current state is Q, input is 0, top of the stack is S. So that means we can choose from current state Q and top of the stack is S. So that is only one production 0 BB. So in the place of S we can replace with 0 BB. So that's why this S is replaced with 0 BB. Next, current state is Q, input is 0, top of the stack is 0. So that is nothing but Q comma 0 comma 0. From ID instantaneous description 3 we can perform the pop operation. That means stack contains 0, B, B, one more B also. So this top of the stack will be popped from the stack, remaining the stack contains 3 B's. At the same way, next input is Q and top of the stack is B, and the Q comma B combination contains 3 productions, and here the current, so that's why we choose whatever the our required production based on the current input 0. So here there are 3 inputs and 3 non-terminals. That's why we can choose in the place of B only 0. In the place of B we can choose this one, Q comma 0. In the place of B we can push 0 into the stack. So next, so now the current state is Q and input symbol is 0, and top of the stack is 0. So as for ID3 we can perform the pop operation. So here as for ID3 we can perform this 0 can pop from the stack. Next, current state is Q, input is 0, top of the stack is B. So that's why you can simply replace this B with 0. So that means this B is replaced with 0. So then next, current state is Q, input is 0, top of the stack is 0. That means 0 comma 0. So that's why we perform the pop operation. So this 0 will be popped from the stack. So then remaining is B only. So now next, input is Q, sorry, current state is Q, top of the stack is B. So that's why okay, input is 0. So that's why we can replace this B with 0. So that's why Q comma 0 comma 0 as per ID 3. So as per ID 3 we can perform the pop operation, that is Q comma epsilon. So here this 0 will be popped from the stack. Now stack is empty. So finally the stack is empty. That's why that particular string is accepted by the PDA. So the given string 0 1 0 power 4 is accepted by PDA. So these are the details about how to convert from context free grammar to PDA and some example. Thank you.